Just a quick introduction maybe to our company. We were founded in 2014. We're based in sunny San Diego, California. Over the years, we've built many different AI and machine learning solutions for a broad range of applications. You heard a little bit today about our models that we built for predicting drug response based on transcriptome profiles. We also have a really long relationship with the company where we've built machine learning models and software for an EKG device, where you can predict cardiology outcomes that normally would only be accessible using echo. So it's a much simpler kind of way of predicting whether somebody has a heart condition. We've done a lot of work with UCSD in a center in Denmark on applying graph algorithms to biomedical knowledge mining. And then last year, we also published actually a paper with Scripps here in town on applying machine learning to improve the accuracy of peptide docking. And this was a really nice collaboration. And I believe that eventually these models are actually going to be available in Autodoc. So I know that the PI is working hard on integrating that into the software. So in 2019, we started a program where we wanted to develop an AI platform for peptide drug discovery. And this platform has been funded by the National Science Foundation. And we are already applying this to commercial data sets, including with one pharma partner. So first of all, why would we want to actually use machine learning for peptide drug discovery? Well, as you probably know, because you're in this field, the data sets are becoming much more complex. They're not just longer, but they're actually wider. So there's so many metrics that you need to kind of achieve nowadays to take a peptide to the next level. It's not just about activity, but it's about selectivity. Very often you're dealing with pathway bias nowadays. You have to have the peptide that is stable, soluble. Nowadays, people actually require cell penetration as one of the metrics that they need to achieve, right? So this is becoming very complex very quickly. We can essentially help use machine learning to really help analyze these complex data sets. We can also accelerate development timelines by prioritizing which compounds you should test in the wet lab that have these characteristics and have improved performance. And even though machine learning is thought really as a black box, you can actually lead to a lot of knowledge gain by analyzing the features that are the key performance drivers. And I'll show you that a little bit later. Machine learning can also lead to a reduction of wet lab costs. If you develop early on predictive models that incorporate the peptide, compound properties and also the in vitro assays, it's going to be much easier to decide which compounds to move to in vivo models. So at the end of the day, you can actually save quite a bit of money. And the last one that a lot of people actually fail to appreciate is that even if your program is close to completion, you can analyze the data sets and you can find non-obvious modifications that you should get data on. Because if you don't get data, you're not going to be able to get broad patent protection. So the last thing you want is to spend all this time working on this amazing new molecule and then not realize that 5 years down the line, somebody's going to come up with 2 substitutions that work around your patent, and you could have actually easily gotten the data. So with our AI platform, we have actually developed it so that we can directly utilize the data sets that are generating during a peptide drug discovery program to train and tune machine learning models. There's a variety of data sets that we can utilize. So this can include, for example, phage display, where we take very complex, very noisy data sets to train models to find true positive hits. We can use we've done a lot of work with in vitro assays where it's just EC50 values for hundreds of compounds, or stability or solubility data. And we can also put in vivo data into the system as well. So once we've built a model and we've decided that it has sufficient performance, as I talked about in my intro talk, we can then analyze which are the features that are actually the key performance drivers, which positions or binding patterns drive the performance. And I just want to point out that if you haven't seen, and I really appreciated Joseph's talk at APS actually, because Joseph's work has done really great job in showing binding patterns for some of the peptides that they're getting, some of the groups of peptides they're getting from their mass spec approach. So I just want to give a shout out to your work because this was really fabulous. I really enjoyed that. The last thing that we do, of course, is we take the machine learning model and whether we can predict novel peptides, right? So these are peptides that you haven't tested yet. We can take the machine learning models and predict and prioritize which peptides should be tested next in the wet lab. And the last piece that we've developed, and this is after talking to a lot of people, is we developed essentially a module that helps not only prioritize for performance, but also prioritize for diversity. And so the idea is to not always just test the peptides that are the best, but actually test a diverse variety of peptides. Some of them may not be absolutely amazing, but they will help you actually build better machine learning models, where on the next round of predictions, you will be able to do better because you've generated diverse data sets. So hopefully that kind of makes intuitive sense to people. So now we get into this question of how do we represent a peptide to a machine learning algorithm, right? And so we've developed 3 different types of encodings at Calibre. And the first type of encoding is what we call the classical feature encoding. And this is where we take the peptide and we break it down into, for example, composition or physiochemical or structural features. The advantage of this type of encoding, and so just going back to my intro talk, just like we took a house and we broke it down into square footage, a number of bedrooms and location, this is exactly what we're doing for a peptide. We're taking the peptide sequence and we're saying, what is the hydrophobicity? What is the charge, the size of the residues, the surface area? And we can do this on a composite basis, meaning for the entire peptide, but we can do it also on a position-specific basis, which is much more detail-oriented, so to speak. So the advantage of this type of encoding is that it's highly interpretable. You can actually go back, especially if you've done this on a position basis, and you can say exactly what is driving performance. The other advantage of this is that it's highly flexible. So if you have custom features like linkers or conjugates, or let's say you're using just a couple of natural amino acids, you can very easily encode this into this scheme. It's also suitable for small data set sizes. So if you have small data sets, you can control the number of features that you create here to at least get you some starter machine learning model. The second type of encoding is a deep learning based encoding. So just like we presented, images to machine learning models, we can also try to represent the peptide in its kind of native representation to machine learning models. And we've developed a set of encodings, and I'll go over them in a little bit. But the whole idea here is to leverage larger data sets. So this is really suitable for things such as library approaches like phage display or mRNA display or other approaches. And to leverage those large data sets to get higher performance. So that's really the goal here. Now at Calibre, I think one thing that differentiates us from other companies and what's also been published is we've really kind of very quickly launched specific sets of encodings that can also handle unnatural amino acids. So this is one of the capabilities that we have right now. We'll be able to talk about it a little bit more, hopefully in the coming months at some of the conferences. The last type of encoding is the design space encoding. And so this is, and Joseph also referred to this a little bit, and I know you guys use it in your work. These are these low dimensional embeddings, right? Where we take the universe of the peptide design space and we embed it into low dimensions because it helps us to visualize the data in a very simple 2D or 3D plot. And so we also have a set of these tools, and these are very useful for visualization and exploration of the peptide design space. So we have validated our platform in a lot of different applications. And so NSF funding gave us an opportunity to really kind of develop peptide immunogenicity models. And we went far beyond just predicting MHC1 or MHC2 binding, which has been published by many groups. But we actually built T-cell activation models where we're able to differentiate Th1 versus Th2 responses. So we're really kind of trying to differentiate pro-inflammatory versus anti-inflammatory type of responses. We've done extensive validation on this. I'll show you a little bit of work on the immunogenicity today, but I'll mainly really focus on the antimicrobial peptides because we just have more data that we can share at this point. With a pharma partner, we worked on bias agonism, and then we have collaborations on phage display where we're applying this platform to identify true hits with at a higher rate and also design better hits directly from those data sets. Like I said, we're also working with the natural amino acids right now, and the initial application is for predicting peptide stability. So before I go into the wet lab validation with the antimicrobial peptides, I just want to give you just a really brief overview of what we've done with immunogenicity prediction. And so the data sets that we're using is effectively immune activation of T cells using various peptide antigens. This has several different applications. This is important for vaccine development where you do want immunogenicity. So even including for cancer vaccines, right? This is very important for that reason. There's also situations where you want to understand this because you don't want immunogenicity, right? So if you're developing a peptide drug, you definitely don't want immunogenicity. But this is also, from a research perspective, is important in understanding various inflammatory diseases. The data sets that we utilized were peptide sequences and the corresponding cytokine release assays. So an example of a data set that we used was 3,000 peptide variants and their corresponding cytokine release assays. The peptides were between 9 and 24 amino acids, and we labeled the peptide 1 as in responding if a cytokine was detected, and 0 if it wasn't detected. We take 90% of the data to train the model and hold out 10% of the data to evaluate the machine learning models. And so, I'm not going to go into details of how we evaluate performance. Hopefully now you understand how we can utilize these confusion matrices of actual versus predicted values to quantify performance. But this, for example, shows you the different feature sets that we can use when we encode peptide using our classical feature encodings and when we apply different types of algorithms to build machine learning models. So we can quantify accuracy, AUC, sensitivity, specificity, and then depending on what we need, we can choose a specific model. So if we want the highest sensitivity model, we would effectively represent the peptides as trimers. If we want really high specificity, actually what's surprising is amino acid composition alone gives us really good high specificity in this situation. But as so before I go into the deep learning aspects, I just want to show you that this is going back to Joseph's questions of like, why would you want to actually utilize these relatively simple ways of encoding peptides? And it's because we get a lot of interpretability information. And so what we can do is after we've built the machine learning models, we can look at the weights of the features in these models. And in this case, we've built models to predict Th1 responses, which are pro-inflammatory responses, and Th2 responses, which are anti-inflammatory responses. And what we can clearly see is that there's different features that are driving those two responses. So for example, for the pro-inflammatory responses, generally the secondary structure and the solvent accessibility and hydrophobicity of the peptides results in Th1 activation. But for Th2 activation, we actually see charge and polarity as kind of the key drivers. And so this is really interesting because you can kind of start to think about what are the different mechanisms that are potentially activating T cells towards one pathway versus another. So that's really kind of, nice. It's nice from the perspective of interpretability. But as I said before, when you get to really complex data sets, especially phage display, these simple models that we build using classical feature encodings, they just fail to get us the sufficient performance. So what we ended up doing is we actually spent a lot of time developing deep learning based networks for peptides specifically. And the whole idea, if you remember this from my intro talk, is to allow the algorithm to learn progressively more complex features at the different layers of the network, right? So the question then becomes, how do we represent the peptide to the machine learning algorithm? With images, we represented it as 0 to 255 values for each of the pixels. With peptides, what people have done before is they know that there's 20 amino acids, so they create a channel, just like you have RGB in images. They create 20 channels, one for each amino acid. And then along the length of the peptide, you can say, if a certain amino acid occurs, I'm just going to give it a 1, and I'm going to fill the rest of this matrix with zeros. So effectively, this peptide sequence right here, this is, I believe, a 9-mer, becomes this matrix of 20 by 9 ones and zeros. So, as a chemist, you look at this and you're like, okay, that's great. From a machine learning perspective, it's actually not so good because it's sparse, it's large. But there's another issue, right? You've completely erased all the chemical information of those amino acid side chains. So you've basically turned side chains into just ones and zeros. And what happens is when you represent the peptides this way, yes, you will be able to build a machine learning algorithm, but you need a lot of data because it first needs to learn about what an amino acid is. So one of the things we've done at Caliber is we've actually spent time building peptide encodings that capture that physiochemical information and the chemistry of the amino acids in a very compact way. We also capture evolutionary information of how the amino acids are exchanged in proteins. And so what we showed is that when we look at two different data sets, one in orange and one in blue, and we compare the performance of our encodings compared to this one hot encoding that I just showed you, in almost all instances, those encodings actually outperform. There's situations also where one encoding is much better than the other. So by having a lot of options available, we can actually quickly pick an encoding that is good for that specific application. The other thing that I want to point out is this issue of dataset size, right? So the smaller the data, the lower the performance. So you can see that this one hot encoding goes from 74%, this is F1 score, to like less than 66, so 65. So a huge drop in performance as you reduce the dataset size. But because we've encoded the chemistry of amino acids, a lot of our encodings actually maintain that performance even as the dataset sizes get much smaller. And so this is kind of the power of our AI platform. So the last thing I want to show you is I want to just quickly kind of take you through some of the wet lab validation data to show you how we have applied this to discovery of novel peptides. So what we did is we took existing data sets of antimicrobial peptides that people have published. And if a peptide had an MIC value below a certain level, we called that peptide antimicrobial. And if it had, high MIC value, then it was non-antimicrobial. We utilized a set of diverse variants between 6 to 40 amino acids, so very large range in terms of size. And so we built the classical encoding models. And like I said, antimicrobial peptides are really easy to predict. We got pretty good AUC values, 94%. But then when we go to deep learning-based models, because they can extract additional information, we see a boost in performance. So we get 97, 98% AUC values with the deep learning-based models. What we can do is we can go and look at the classical feature encoded models, and we can figure out very quickly what is driving AMP activity. And what we can see is from our encodings, classical encodings, is that charge and solvent accessibility were kind of the key features of the peptide that made those peptides as antimicrobial peptides. This is not surprising, right? So then what we can also do is we can actually visualize, for example, peptides that are antimicrobial and non-antimicrobial using what are called spiderweb plots, right? So we can take, for example, the classical encodings where you just encode peptides as the types of amino acids, right? So we have buried amino acids, aliphatic, basic, acidic, aromatic, small. So you can essentially take a peptide and you encode it as the frequency of these types of amino acids. So for example, this peptide right here would have 0.6 amino acid frequency of aliphatic amino acids. And so very quickly, by just showing the peptides in this manner, you can see what are the features of antimicrobial peptides versus non-antimicrobial peptides. And so these are the top AMPs that are predicted by the models. But what's really cool about this visualization is you rapidly see that the AMPs are all very similar to each other, right? All of these curves, these are, I think, 10 or 20 AMPs. They are almost on top of each other. They have very similar profiles. But if you look at non-AMPs, they are all over the place. They're very diverse. And so using these visualizations of even classical features, you can very quickly kind of see patterns in your data. So what we wanted to do is we have these machine learning models, right? And we wanted to see, can we discover novel peptides, novel antimicrobial peptides? So we just used, we just scraped some data off of the web of natural peptide sequences, right? And we predicted them through our models. So we predicted 1,000 peptides, and then we took 30 peptides that span the range of predictions from low activity to high activity. And we went and just synthesized them and tested them in the wet lab. So these are the predicted values on the relative scale, and these are the actual values. And what we found is we basically had 90% accuracy. So we had only one false, this was a false positive prediction, and this was a false negative prediction. We had 8 peptides, 8 novel peptides that we found that had decent antimicrobial activity. And we had 3 peptides that had moderate antimicrobial activity. And so overall, pretty good results from a machine learning perspective to take 30 peptides and actually get 90% accuracy of your predictions. But then what we wanted to do is we wanted to push this further, right? So we said, can we take some of these hits that already have good AMP activity, and can we actually make them better without generating additional data? So just by using our models to predict modifications. So then what we did is we predicted modifications to those peptides anywhere from 1 to 7 amino acid mutations. So this is really kind of going far into the space. It was up to 3 substitutions and truncations, right? So this is how we come up with 7. We wanted to make some of these peptides shorter because they were, over 20 amino acids. So we wanted to truncate them. And so these are results for 2 hits. So KB10 was one of the hits that we found, and these are the mutations that we made. So for example, this V1 had 2 mutations. This was just a truncation. And this is the prediction. So we're predicting whether the MICs will change by making it, less of an antimicrobial peptide or more of an antimicrobial peptide. And this is the fold activity change that we saw compared to the wild type sequence. And so in the case of KB10, 7 out of 8 predictions were correct. And we were able to find a mutant peptide that was truncated and had some substitutions that had an 8-fold increase in activity. In the case of peptide 25, 8 out of 9 predictions were correct. And we found a double mutant that had a 32-fold improvement in MIC values. And so we were able to predict multiple mutations at the same time. But all of this was done without generating additional data. So just still using those original models that were built. And what we can do, of course, is we can visualize all of these substitutions and these heat maps, right? So we have a peptide, we have a position, and at each position, we can mutate that peptide to all the different amino acids, right? And what we can very quickly see is we can quickly see positions where modification of that amino acid to any other amino acid is going to lead to a loss of activity, right? Because blues basically represent a decrease in activity and reds represent an increase in activity. What we can also see with this kind of global picture is which substitutions the algorithm kind of believes are the best. So in this case, in position 5 and 6, it really wanted to put a tryptophan in there. But we said, you know what, peptide with a lot of tryptophans. I'm not a peptide chemist, but I've heard people complain about tryptophan. So I said, let's put phenylalanine. So we put phenylalanine in there, and it was still much better. So this had an 8-fold increase in activity. And then in the case of another peptide, this is another triple mutant that had a 32-fold increase in MIC activity. So in addition to overriding the algorithm, these heat maps also give you kind of a quick global picture of what's happening in each of the positions. And this is also what we can use to help people get broader patent protection. If we see a modification that they haven't tested that could potentially allow a competitor to work around it, we would definitely point it out and say, hey, maybe you should get some data in this position because it's still a really good peptide. And so the final kind of data slide I want to show you, and this is a slightly kind of separate story, but I just want to quickly share this with you because this question of data set size keeps on coming up over and over again. So we wanted to see, can we push the limits of data set size in terms of building machine learning models? And so we had this AMP data, right? So we had basically 100 positive antimicrobial peptides and 1900 negatives. So we had existing wet lab data, and we wanted to see how quickly could we find these positive peptides if we were in a screening situation, right? If we didn't have this data ahead of time. So we wanted to see, can we use the AI to prioritize which peptides we should test when we're doing screening? And so we set up this screening simulation where we compared the ability of our AI platform to pick peptides to screen compared to just random wet lab screening where you just pick up another 96 well plate. So in the first round, we screen 100 peptides, and we know what the frequency of the positives here is, right? And I'm just showing you like the average results of an average simulation. So we get 6 hits each for both of these methods. And this is not surprising. They don't really have any information at that point. In the second round, we use the AI based on these 6 positive hits to prioritize which 34 peptides we're going to test in the second round. And what we saw is we saw a huge enrichment in the number of additional positive hits that we found compared to random screening. And then by round 4, we only screened 10% of the library, but we actually found 5 times as many hits. We found 50% of the total hits by using the AI to prioritize which peptides should be tested in the subsequent screening rounds. When you show like where those peptides, those positive hits are in the design space, and so we can represent peptide design space in these 3 dimensions, and then show the hits using the larger red dots, where the remaining hits are in the smaller red dots, you can see that we actually find hits throughout all the regions of the peptide design space where those hits occur. So by round 4, we're really kind of nicely covering the design space in terms of our hit space. But really the biggest result from all of this, which surprised me, like I was shocked, was that we build a useful machine learning model with just 6 positive data points, right? This is truly kind of pushing the limits of data set size. I didn't think this was going to work, but I was like, well, let me just try it. And it did. So once in a while, you get surprised. And so I just want to finish up by saying that we have built, we have been working on this for over 3 years. We have built solutions that really cover the entire preclinical development pipeline, all the way from helping people design better libraries using the design space tools, through finding hits from phage display libraries, to lead optimization, both in vitro and in vivo, right? So we've done some in vivo work with very small data sets where we help people prioritize which additional peptides to test. But we've done quite a bit of work with just typical lead optimization data sets where we have EC50 values and other parameters that people are trying to optimize. And then if you don't know our team, here's our team. So you probably know Sumitra Ghosh. He's kind of a well-known person in the peptide field. He's done a lot of work basically at Amylin, right? So a long tenure at Amylin. And then I work with Adrian Day, who runs the Peptide Therapeutics Foundation in San Diego and spent a lot of time at Ferring. And then Leonard and Keith are kind of the software gurus in the on the team that help kind of take some of the code that I develop and make it pretty. That's basically what they do. And that's all I have. So I'm happy to take questions and talk about any other topics.